Hey everyone, this is going to be an interesting video because this is a new emphasis we're going to try to introduce. In the past, we've just kind of had a unit where we talked about ionic bonding, and then we had a unit where we talked about covalent bonding, and we really kind of forced a disconnect with what we were trying to accomplish. When we get to intermolecular forces at the end of the covalent unit, students have been left with the impression that intermolecular forces are in everything. And we even say that, it's teacher fault. But as I was explaining to my AP classes at the end of this current school year, and I realized they had that misconception. I realized the fault was mine because I should have taught them to first identify what type of substance you're dealing with, because some substances don't have to worry about IMFs. Some substances are in a crystal structure held together by ionic bonds and covalent bonds and metallic bonds. So I want to take this opportunity to go through that and start getting you guys to think about first determining what type of substance, what type of solid you're dealing with. Then we can worry about why is it a solid, what's making it a solid. So as we talk about types of solids, let me first tell you that there are four types. There are metallic solids. These are solids held together by metallic bonds. We have ionic solids, which we've already looked at before Christmas, held together by ionic bonds. There are molecular solids and covalent network solids. Each of these are held together by covalent bonds, and it's a different process that makes them a solid. Here's a summary. Everyone should have this page printed out or given to you as a handout in class or on Google Classroom, but it needs to be in your notebook. As we look at substances, your job is to determine what type of substance it is and then identify the properties it would have. And a lot of times, especially on the AP test, you're asked to predict which substance would have a higher boiling point, or which one would be the most malleable, or which one would be the most conductors. And all of these physical properties that come about are due to the type of bonding in that solid. Again, we are talking about the solid state here. Not gases, not liquids. These are starting with solids, which is the most crystalline, regular arrangement, and really kind of the easiest of the states of matter to discuss. So just kind of going through this real quickly, molecular solids, these are going to be the ones that have our IMFs, which we'll get to at the end of this current unit. So IMFs are important for molecular solids. These are going to be your weakest solids. These are going to be the ones that are easiest to melt. These are going to be your softest things. They don't conduct. And then you have covalent network, which are also covalent bonds, but these are super hard. These are going to be nice, pretty crystals, high melting points, very hard. Also poor conductors because of the covalent nature. But think of diamond, quartz. These are really, really strong bonds. Very similar to ionic. We learned ionic before Christmas. These are when you have the positive negative attractions, according to Coulomb's law. Ionic are also very hard, ionic solids. They're very hard, brittle, high melting, high boiling, very similar to covalent network. And they also have a pretty crystal structure. So covalent network and ionic are often confused for each other. What you're going to be able to do is identify ionic from the presence of a metal in the formula. Like here, calcium nitrate, there's a metal, calcium. And then finally we have metallic solids. So these are going to be held together by metallic bonds, which I'll explain in a minute. There's a very wide range of metallic bonds, from soft, think of cesium or sodium, to very hard, think of tungsten, think of iron. And you can have low melting points, again, think of cesium, to high melting points, again, think of tungstens in the filaments of your light bulbs. And then we have varying degrees of electrical properties, malleable, ductile, and I'll explain what happens in metallic bonds to cause that briefly. But these will be all of your metal elements and your alloys, such as bronze and brass and so forth. So again, print this off, put this in your notebook. Let's begin by talking about metallic bonding. You can see here a picture of gallium. You'll know a metal, it has that typical lustrous crystalline sheen, and yes, this is a crystal. So metallic bonds are when you have atoms that have low ionization energy, so they give up their electrons easily, low electronegativities. What happens is that the electrons kind of go into this delocalized soup, this fog, this sea, whatever metaphor you want to use, and then the positive, not just the nuclei, but the positively charged nucleus plus the inner core electrons, the non-valence leftovers, if you will, kind of sit there like islands in the stream. And the electrons, the valence, are given up and they are delocalized, so they're free to move about everybody or everywhere. This is a crystal structure because there is a regular pattern to where the positive charges are placed in relation to each other. In the old days of chemistry, we would actually stop and have about a week here to talk about the different types of crystal structures of the metals. You would hear things like close packed or cubic centered cells. We don't teach that anymore, not because it's too hard, but because it's just too much to fit into a year. Many of you will never see that. Some of you will see it in college chemistry, depending on who your professor is, and some of you who go into more of the material science, mechanical engineering, chemical engineering, and other things will get a chance to learn about that stuff later. So in those metal solids, we talked about the valence electrons form a soup, a delocalized soup, and that soup kind of acts like a glue that holds everything together. It's kind of like laying down this long bead of glue and adding a bunch of bedazzled stuff to clothes or a hat or something, if you've ever done that. Obviously I haven't. Some people use Rice Krispies as an example. I think this is a horrible analogy. I think the plum pudding analogy back to the electron that we talked about the first semester is a little bit better, though not quite the same thing, but it's right on the right track. So what are the properties? Malleable and ductile. The reason metals can be flattened or stretched into wires and not come apart is because that soup, that fog, that electron sea is bendable. The electrons are not locked into position. Also, metals can conduct. Again, the electrons are free to move. One electron in, one electron out. That's what conducting are. If the electrons are locked into place, like in ionic bonds, then we couldn't go anywhere. We couldn't conduct. They're shiny because the electrons in that sea are free. And then so when they absorb energy, they oscillate at the same frequency as light, and then they emit light backwards. And it looks like a reflection, but it's really the electrons re-emitting some light. They are solids, and this is important. They are solids because metallic bonding is pretty strong. It is a type of I-N-T-R-A, intramolecular force. And these are always stronger than inter. That may not make any sense now, but by the end of this unit, it will. And these intramolecular forces are fairly strong, so it keeps all those positive bodies of the metal atoms near each other. So they are solids. Mercury is the exception. It's just a weirdo. No one really has a good explanation for why. Metallic compounds are pretty hard. That depends on several factors. So melting and boiling points, talked about those being pretty big. What are those factors that I'm talking about? Well, the difference in different metals, the main two factors are how many valence electrons are being donated by the atoms. So the more valence electrons that you're able to donate to that electron sea, the stronger that sea becomes. In other words, the stronger the glue becomes. And so you have higher melting points, higher boiling points, and they're usually a little harder. Another factor that's important is the atomic number. For the S block elements, the most important thing with atomic number is the atom gets bigger the further away. Coulomb's law says you have a weaker hold. But for the transition metals, as you have a larger nucleus, more protons, you have a larger positive charge, and that actually makes it stronger. So as you go toward the bottom of the transition metal group, those metals are typically harder, and they have higher melting points and boiling points. So here's a final picture of the electron C. This is the way I want you to think about it. The blue parts would be the valence electrons, and the positive parts are the nucleus plus the leftovers. There are some electron inner cores there. And then an electron is free to move anywhere in this entire crystal because they are delocalized. All right, I'm going to talk just briefly about ionic bonds because we have already covered this. In the ionic bond, you have transfer of electrons that create the ions, and then these ions interact according to Coulomb's law in an electrostatic attraction. We've talked about what makes ionic bonds strong, and the two factors that we talked about before Christmas was charge, that's the Q in a Coulomb's law in the numerator, and then the other factor was how far apart they are. Larger ions make weaker bonds, smaller ions have stronger bonds. That's the distance factor in the denominator of Coulomb's law. If you don't remember that, hit pause, go look up the Coulomb's law from earlier notes, and let's get back on because I'll be referring to it again. So ionic solids held together by these ionic bonds are also crystals, and they form the crystal lattice that we talked about. And when we do ionic formulas, really what we're doing is finding the empirical formula. We're finding the formula unit, the simplest ratio of cation to anion. There's lots of different types of crystal lattice structures. We can have simple cubic cells where there's just like an atom in the corner, each corner of a cube. There are face-centered cubes. There are body-centered cubes, and this could go on and on. It can be quite complex. But again, we don't have time to learn all that stuff. So here's what I was talking about: body-centered, face-centered. I did not mention hexagonal, but we can have other than cubes. You can have hexagons, octagons, and so forth. And each geometry has its own set of strengths. But ionic bonds and ionic solids, such as the one you see here, sodium chloride, are also very strong. The bonding that holds it together and makes it a solid is ionic. And ionic is even stronger than metallic. So as a result, ionic compounds are solids. They are soluble in water because the ions can interact with polar water and form ion dipole forces that we'll learn later in this unit. But they're brittle because they're in this lattice. There's no give. The electrons are locked into position. They can't move. So if I put enough force and cause the ions to shift relative to each other, they can get far enough away that you have a break in the bonds. So they are brittle. They will not conduct electricity, again, because the electrons are locked. But if I liquefy it and break it out of the lattice, then it will conduct again. And then they have the high melting and boiling points. All right, so now we're getting into the more complicated stuff. Covalent bonding. I mentioned earlier that there's two types of solids through covalent bonding. One's covalent network and the other is molecular. We can see here in this picture that when we have covalent bonding, unlike ionic, where they're positive, negative, and they attract over a distance, the ions never actually touch. In covalent bonding, there is a little area where the two atoms are touching a little bit. Their electron clouds are overlapping somewhat, and the electrons are locked into that overlap area. So they're not quite the same as ionic, but it's very similar in properties. So these covalent bonds happen when you have, like I said, nonmetals, typically high ionization energies, So they don't want to lose electrons, they prefer to gain because they have pretty big electronegativities. And we're going to learn more about this in the current unit, so I'm not going to spend a lot of time about it. In the next few slides, talk about polar and nonpolar. I don't want to do that in this particular PowerPoint because it's going to convolute my main idea. So let me just kind of scroll through and let's get to this covalent network. So this is one of the two types of covalent solids, covalent network. It's the hardest one for you to understand. Covalent network are almost exactly like ionic. The main difference is that the bonds are covalent. So you don't have forces acting over a distance, you have the electrons being shared. So the things actually touch a little bit. But the overall effect is a nice, pretty crystal that has almost all the same properties as ionic. Properties such as high boiling point, high melting point, brittle, hard, don't conduct. And let's compare carbon dioxide and silicon dioxide. So these two compounds are are made from elements in the same column, group 4. So we would expect them to have similar properties, but they don't. It turns out that silicon actually has an astoundingly higher melting point and boiling point compared to CO2. Why is that? It's because silicon dioxide is allowed to covalent network and form a crystal through these interacting covalent bonds, but CO2 is a molecular covalent, and it only gets to become a solid through weaker, much weaker IMFs, intermolecular forces. So that's a very big, important distinction. Here's an example, or a picture I should say, of silicon dioxide, raw sand. And then, because you can't really see the pretty crystals when you look at raw sand, but if you look at silica glass, which many of you have seen, you can start seeing the crystalline structure here. And it looks more like an ionic salt. So a covalent network solid, again, is a solid that consists of atoms held together by interconnected chains of covalent bonds. And it's allowed to go into extra dimensions, usually 3-dimensional. You can make some 2-dimensional, but usually the real distinction here is 3-dimensional. Graphite is a definite example of one that does a 2-dimensional network, and I'll show you a picture of it. But here's some examples. Diamond, graphite, silicon, asbestos are all covalent network. These are going to be very strong. They're so strong, covalent bond, pure covalent bonds are a little bit stronger than ionic, so you're going to see slightly higher melting and boiling points for these compounds compared to ionic. They're not going to be soluble in water because there's nothing for water to attract to. There's no ions here. These are just atoms sharing electrons. And again, they do not conduct electricity because, like ionic, the electrons are locked into position. So here's just some pictures of some covalent network. They're still crystals. Maybe not quite as easy to see the crystals in everything, especially these carbon compounds like graphite. Graphite to me is not a pretty crystal because of the opaque color, but that's not really its fault. Here's a picture of graphite. It doesn't look like a pretty crystal. These are actually 3 different sheets of graphite. The way pencils work is that you have these interconnected carbon atoms. So let's look at the red one at the top. These are all carbon atoms in hexagons that are all interconnected. So that is a covalent network. In your pencil leads, the graphite stacks up like layers in a cake, and these layers are then connected by these dotted lines through intermolecular forces. So this is a 2-dimensional lattice. When you write, friction breaks these dotted lines, these weaker bonds, and it leaves behind the graphite on your paper. So you're leaving behind a covalent network solid on your paper. Diamond is another allotrope of carbon. Instead of 2 dimensions, though, it goes into 3 dimensions. And you get that nice, clear, beautiful crystal with diamond. Now, finally, we can talk about molecular. Our covalent unit this year that we're currently starting is really molecular covalent. That's what we're learning. That's going to be the Lewis structures that we draw, the geometries that we learn, the intermolecular forces that come along with it. Because so many more of the compounds that you interact with daily are molecular. That's just common organic stuff. These are molecular compounds, molecular covalent. This is really different because these don't typically form. They can form a crystal, but they don't typically form the crystals that we think of with ionic and covalent network and metallic. Instead, molecular covalent molecules form from covalent bonding, and it forms kind of the skeletal structure of the molecule, like water. H and O bonds together covalently. Now an H2O then becomes a molecule. So think about it as a ball, okay? And that is a discrete molecule. If you want to make water a solid, then you have to bring in more water molecules. Again, think a bunch of balls here. The thing that makes it a solid would be now not covalent bonds between different water molecules, but static, intermolecular, electrostatic attractions between the different molecules. So molecular compounds, molecular covalent compounds, are only able to become solids through the action of intermolecular forces, not the super strong intra of ionic, covalent, and metallic. I understand that you may still have some confusion there because I'm saying covalent too much. The difference between covalent network and molecular covalent is that in a covalent network, the covalent bonds connect everything to each other. It's like a chain reaction of covalent bonds. Everything's connected. But in molecular covalent, you use covalent bonds to build the molecule, think ball, and then the different balls get attracted to each other through electrostatics only, not covalent bonds, electrostatics, and that's a much weaker thing. So the properties of these molecular covalent things are going to be lower melting and boiling points because you only have to break the IMFs, not covalent bonds, to change state. They're going to be soluble sometimes, depends on whether it's a polar compound, we'll learn that in this unit, or non-polar. And they also will not conduct electricity. So we're going to stop there. That's the main idea. We're going to look at a compound. We have to decide whether it's ionic, metallic, covalent network, or molecular. If it's one of the first 3, ionic, covalent network, or metallic, then we can use ionic, covalent bonds, metallic bonds to discuss the properties. If it's a molecular covalent, it's a different animal because we have to talk about intermolecular forces, and that's ultimately the goal of this current unit. So when we come back in the next little video, we'll have some practice where we look at molecules and try to identify what type of bonding is going on.